So a limit at infinity, what exactly is a limit at infinity? Well, if you have taken or if you are taking calculus, then you have an idea of what a limit is. So you know that the limit as x approaches c of x equals c in general, right? So that's the intuitive definition. It's not really the formal definition. That's the epsilon delta, which goes beyond the scope of this video. But the intuitive definition is that the limit of x equals approaches c of x equals c. Now, this might seem familiar to you. Now, and let me get my red dot real quick. So yeah, this might seem familiar to you, but if it isn't, then that's fine, because the limits at infinity, unlike other types of limits at infinity doesn't really involve much calculation. It's very conceptual. You could just find the answer from looking at it. And if anything, it's probably like the basis of calculus, or I don't know if it's the basis per se, but it's probably the most basic concept in calculus. And also it forms the foundation of calculus 2 when you start doing tests for convergence, converging and diverging series or functions. So how do we go about this? Well, when you're finding a limit at infinity, then there are a few rules that apply, and I'll elaborate them as we go. So rule number 1. Rule number 1, or step 1. If A is greater than B, limit is infinity. Step 2. If B is A, limit is 0. Rule number 3, or step 3. If A equals B, divide by the degree, let's rewrite this. Divide each monomial by the leading degree. Leading degree, then evaluates. All right, so that's those are the general rules for finding limits at infinity. So what does all this mean? You might be asking. I should probably draw the better box. So what does all this mean? You might be asking. Well, I'm going to give you a few examples as soon as I draw this better box. And this is very helpful to write down if you're taking notes. Pretty much everything I've written so far. So let's use an example. So for number 1, let x, the limit is x approaches infinity of x. So replace c with infinity. So limit as approaching infinity of x equals, well, just infinity. And I believe I forgot to elaborate this earlier, but a and b, those refer to the degree of the, so a is, I guess I should write that. A equals degree of numerator, and b equals degree of denominator. So in this case, there's only a numerator, there's no denominator. Or you could say that this is x to the power of 1. You could write it like this: x equals x to the power of 1 divided by x to the power of 0. If you want to really think about it conceptually. So the degree of the denominator is greater than, so in this case, a is greater than b. So it's just going to be infinity. Because remember, x, anything to the power of 0 is 1. And yes. So basically, you're dividing x by 1. And as x approaches infinity, then so does y. So when you sketch this out in a Cartesian plane, then it looks like this. Oops. And in fact, let me draw the straight line. At least let me try to. But it looks like this. Scratch that. That's not going through the point of origin. Looks like this. And then I can clean up these tick marks here because they're no longer necessary. To the best that I can, I'm going to accidentally delete the graph, but you get the idea. So remember, this is y equals x. So for every x, there's this equivalent y value, or every input value there's an equivalent output value. So when x is 1, y is 1, 1, 1. When x is 2, y is 2, and so on and so forth. X is 0, y is 0, cross through the point of origin. At least it should. I didn't draw it perfectly, but I'm sure you get the idea. So as x approaches infinity, so this is, if you keep going in this direction, then you eventually reach infinity. It just goes on forever. As x approaches infinity, and so does y. Because going this direction, it's also infinity. It just goes on forever. So there you have it. That's the first rule in action. Now let's go through the second rule. So at the limit as x approaches infinity of, let's do 1 over x. That's too far from the function, or the limit. 1 over x. Now again, you could write it like this too. 1 over x equals x to the power of 0. So then basically an inversion of what I did previously, divided by x to the power of 1. So what have we here? Well, the degree of the numerator is less than the degree of the denominator, or the degree of the denominator is greater than the degree of the numerator. Take your pick. It's the same thing either way, thanks to the commutative property. So what does that mean? Well, let's look at the rule here. If b is less than a, the limit is 0. Let's sketch a Cartesian coordinates and see to verify this. So you remember asymptotes, right? Well, this is an example of a function with asymptotes. So when x is 1, y is 1. When x is 2, y is 1/2. When x is 3, y is 1/3. X is 4, y is 1/4, and so on and so forth. And then when x is 1/2, and 1 divided by 1/2 is 2. And then it's 1/3, 1/4, and so on and so forth. That's not. Gotta draw this better. But yes, it goes on to infinity. And you remember asymptotes, right, from algebra? Let's draw an arrow here. You remember asymptotes, right? Asymptotes. Algebra and pre-calc. So, oh, and also when you do negatives, this is -1, and this is -1. So -1, and so on and so forth. Yeah, I can do better than that with the arrows. Sorry, I'm a bit of a perfectionist. But anyway, you get the idea. It's, again, it's not perfectly drawn, not necessarily drawn to scale, but it's just to give you an idea. In fact, this, if anything, this should go like this. So it'll be a little closer. Okay, so you remember asymptotes, right? Meaning that it's especially true for exponential functions, or when when you're dividing a numerator by the denominator of a higher degree. And because remember, you can't divide by 0. So let's say x is 0, and it creates an asymptote. But as you get closer and closer to 0, then it approaches infinity, either in the positive or either in the vertical or horizontal directions for either x or y. So I can actually draw this out. The horizontal asymptote for this function is x equals 0, and the vertical asymptote, so the HA and the VA vertical asymptote, is y equals 0. And that's indicated by these dashed lines. So yes, in algebra, you learned that. As you get closer and closer to any of these values, y equals 0, x equals 0, then the function will get closer and closer to either the x-axis or the y-axis, but won't ever touch them. So in this case, we're looking at this part of the function right here. Let me get my highlighter out. Look at this part of the function. So for all x equals, so x is greater than 1. Oops, different color. For all x is greater than 1, then because remember, we're looking at positive infinity. Technically, infinity could cover the entire plane, but specifically, I'm going to look at positive infinity. I mean, infinity from the positive direction. So if you want, I could just if you want, you can put a plus sign right here, but you don't really have to. As x approaches infinity, and technically, this also holds true from the negative direction, but I'm specifically going to look at the positive direction. So as x approaches infinity, it gets closer and closer to 0 without actually touching it. However, in calculus, since calculus is the mathematics of continuous change, we rely on approximations for our results. So you can just say it equals 0 instead of saying that, oh, it's close enough to 0, but not quite. You can just say it equals 0. So, and that satisfies this second rule. If the degree of the denominator, excuse me, is less than the degree of the numerator, back up. If the degree of the denominator is greater than the degree of the numerator, or b is greater than, I actually messed up here. Let me change that. If a is greater than b, or b is greater than a, or a is less than b, either or, then the limit is 0. All right, let's move on to our final example. Erase all this. Erase all this. All right, so we have, last but not least, we have the limit as x approaches infinity of, let's say, 2x squared. Actually, no. X squared minus 2x plus 3. And two x squared plus 1. So we have, so as you can see here, the degree, so the exponents, the leading exponents of both the numerator and the denominator are equal to each other. A equals B. So what you have to do is you have to divide each monomial, or in this case, I'm just going to multiply by 1 divided by x squared. And it's going to look like this. The limit as x approaches infinity of, and these are going to cancel when you after you divide. It's going to be x plus 2. Actually, no, it's just going to be 1. Remember, this is a 1. So 1 minus 2x, back up. Remember the rules of exponents. So it's going to be x to the power of 1 minus x to the power of 2 is going to be x to the power of -1, or whatever, 1 over x to the power of 1, or I guess n in this case, where n equals 2, plus 3 divided by x squared divided by, and actually I need to rewrite this rule. I'll get to that in a minute. Divide by 2 plus 1 over x squared. Then evaluate, so I should have added this, using rules 1 and 2. So now we have, we're back to rule number 2 in this case. This is especially rule number 2. So let me indicate that, highlight that. Now we have 1 minus 2x minus to the power, 2x divided by, 2 divided by x, and yes, and remember that if the degree, or if b is greater than a, degree of the numerator, or if degree of the numerator is less than the degree of the denominator, so a is less than b, in other words, then it's 0. So after you evaluate, it's going to be, change color. After you evaluate, it's going to be 1 minus 0 minus 0, because remember it's 0, 0, 0, divided by 2 minus 0, which simplifies to 1/2. And that's it. Now there is a shortcut to this, and that is, well, if you see that the exponents or the degree is the same, then you just ignore the rest of the equation, and then you take the coefficients, and you take the ratio of the coefficients of each degree, or that precede each degree. So in this case, you have 1x squared and you have 2x squared. So you basically you write it as a fraction, 1 over 2. Now let's say we switch the numbers up a little. Then it would be 2. It would be 2, actually, back up. It would be 2 goes on the top, 1 goes on the bottom. Then in this case, it would be just 2, or 2 over 1 equals 2. Now let's say we did 4 over 3. Or better yet, let's just erase this altogether. Well, we can keep that there, but we could say limit as x approaches infinity of 4x plus 1 divided by 3x minus 2. Then we can just look at, get my highlighter again. Just look at this, 4 and 3. Oops. And then there you have it. 4 divided by 3. Instead of having to do all this messy work. You could do it this way if you want to show your work, but if all you need is the answer, like if your professor or your teacher just asks you for the answer, then you just take the coefficients. And we're done. I know it's a lot to take in, but once you get the hang of it, once you practice it, it's really easy. It's something that you can just do in a snap. And I hope you found this video helpful.